solutions and mixtures is our next section that we're going to talk about. When we have solutions that come in the form of solids, liquids, and gases, we have macroscopic properties that do not vary due to the fact that the solution composition is uniform throughout. Remember, solutions are well-mixed mixtures. So everything in that sample, whether you grab it from here or whether you grab it from there, you should still have the same number of moles in that sample. Does that make sense? Because it's well mixed. It's not like sand and water where the sand's going to settle at the bottom, and if you grab it from the top, all you're going to get is water. And if you grab it from the bottom, you're going to get primarily sand. With a well-mixed mixture, if I grab some right here or I grab some right here, they should have about the same number of solute particles in that sample. That's what this is trying to say. Does that make sense? They're well mixed throughout. For liquid solutions, the solute may be a gas, it may be liquid, or it may be a solid. So for gas, for example, like with pop, you have carbon dioxide dissolved in that pop. That's what you're getting that. Oxygen that fish live off of, it's oxygen that's dissolved in the water. They're not taking, fish don't take the water molecule and split it and use that for their respiration. It's actually oxygen that's dissolved in the water. So if you have a water sample here, you've got water that's, or oxygen that's dissolved in there. Okay. It could be a liquid, like if you've got, have you seen those Mio things where you can add into your water to give you flavorings? That Mio is a liquid, so you can mix that in. It could be a solid, like if you had salt water, that would be a solid that's dissolved in there. So there's different ways of describing concentration. Molarity is the one that we use most often. There's stuff like molality, and you can do mole fractions. You can do other things like that. They don't use molality in AP. They use molarity, those. And you've got to be good with molarity because we use it a lot. Okay, so what molarity is it's abbreviated with a capital M, and it equals the moles of solute divided by the liters of the solution. You need to get comfortable with this guy, and you need to know how to take grams and put them into moles, which you should be able to by now. You need to take liters and milliliters and turn them into liters. All you have to do is slide the decimal 3 spots. A liter is bigger than a milliliter.
Times 5,000.
Times it by, well, you would, if you have milliliters, you're going to divide it by 1,000. Mm-hmm. Yeah. So if you have milliliters, divide it by 1,000 to get liters, but it has to be in liters before you can calculate molarity. All right. The components of a liquid solution cannot be separated using filtering. There are no components large enough to scatter visible light, which is your Tyndall effect. Tyndall effect, remember, is colloids and suspensions when the suspensions are actually mixed thoroughly. So like sand and water, if you take that and shake it, that would show a Tyndall effect right away. But if you let that settle over a course of hours, all the sand's going to go to the bottom, and then it's not going to show the Tyndall effect because all it's shining the light through is the water. And remember the Tyndall effect, the best example of that is fog. So when you're in fog, you are actually sitting inside a colloid. And the Tyndall effect, when you turn on your brights, you're reflecting internally inside that fog, that light. And that's the Tyndall effect. That doesn't happen with solutions. Solutions are mixed thoroughly, and they don't show the Tyndall effect because the particle size is much smaller. The components can be separated using processes that result as a result of the intermolecular interactions between the components. In other words, we could use distillation or we could use chromatography. So distillation is where you would take advantage of the different boiling points of the solution. So if you've got like alcohol and water mixed together, you could heat it to around 80 degrees Celsius. The water isn't going to boil, but the alcohol would. And then you would capture that alcohol in a distillation apparatus, condense it back out, and then that would give you your distillate. So if we look here, this is like what a distillation apparatus would look like. Let's see if I got a better picture here. Show up a little better. So here, if you had like water and alcohol in here, you would heat this to where the alcohol would turn into a vapor, but the water would be left behind. And then it runs down this tube. This tube has an outer tube that has water running through it to cool this gas. And as it cools the gas, it condenses back down to a liquid. And then you can pick up what's called the distillate over here. So your alcohol would be over here. And after you boil this long or get this heated long enough, this would be pure water. This would be your alcohol then. Does that make sense? So it takes advantage of the different boiling points. Which one of these would have lower intermolecular forces, the alcohol or the water? The alcohol. That's why it boils at a lower temperature. All right. Chromatography is another example of something where we can take advantage of the intermolecular forces. And we're going to get to that tomorrow after your quiz. Yes, you have a quiz tomorrow. All right, ion concentration then. Ionic compounds are going to dissociate into ions when they form solutions. So they're going to go into the different ions. So here's calcium 2+, and then we would have had 2 chlorines because it's a -1 to go with that. And what's going to happen is your water molecules will surround this. This is a negative charge, so the negative pole of the water will surround the negative ion. So the positive pole of the water surrounds the negative ion, and the negative pole of the water will surround the positive or the cation. And it does that until one of 2 cases ends up happening. Either you run out of ions to surround, which is a unsaturated solution, or, which is in this case, you've got extra water kind of sitting here off to the side, or you run out of water and you have extra ions left over, and that's called a saturated solution. Yeah. There is supersaturated is a special kind of solution where you can heat the thing up. You can add in extra solute beyond what would normally be available to add in. And it doesn't happen with all things. Like acetates are really common to be able to have that happen with. But you can add more in than it needs. And then it'll stay in solution. But with supersaturated solutions, they are extremely, unstable. Okay, so if you were to introduce one more crystal in to that after it's cooled, it'll go out of solution. Or sometimes just tapping the side of the flask with it in there, just that agitation alone will cause it to go out of solution. So they're very unstable. But the typical situations that we talk about are unsaturated, where we have extra water left over, and then saturated, where we would have extra ions left over. And typically these ions are going to settle out on the bottom of the solution. Okay, good. We talked about how you would have with these, with NaCl, you would have 1 Na and 1 Cl. CaCl2, you would have 2 Cls for every one of these. And you can kind of see that from the formula. S indicates the solid phase. AQ indicates that it's been mixed with water, aqueous, okay? When you go to aquarium, okay, fishies that live in water and other things. All right, Unit 1, we saw how the composition of solutions can be expressed in terms of moles, and I think we've talked about that, right, in molarity. Relative low molarity solutions, there's small numbers of solute particles compared to solvent particles. And in relatively high molarity, there's a lot more solute particles. Again, we can use this distillation. Sorry, this is dilution. My apologies. This is quintessentially a question that's almost always on the exam, is how to dilute a solution down. So you need to be comfortable with that idea. So the first thing that you're going to do is you're going to calculate the number of moles present in the final diluted solution. And moles equal the concentration that you want to achieve times the volume. Then you calculate the volume of the starting solution. The more concentrated the solution that supplies this number, the moles, so take the concentration and the volume of that. The volume of the water that must be added to the concentrated solution is simply the difference between those volumes, but it's not always exact, okay? So when we're looking at dilutions, for example, here, we have to calculate this. So our final solution is we want to end up with, what would this be? 3/2. Final solution must be 2 liters, and they want 3 moles, so 3 molar. So 3 molar solution here, okay? So if you're going to do 2 liters and you want 3 moles, you're going to need 3 moles of KOH. So since the moles of this in the stock solution are available, it's going to have 6 moles, and we have an 8 molar solution, you need 0.75 liters for that. So you're going to take 0.75 liters, you're going to add in about 1.25 liters to make the 2 liters. Okay. And why I say about is because when you are doing these dilutions, you have, sometimes they mix together and it lowers or changes the volume based on how it's going to mix. Okay. So when you're working with these, you have to use something that's a very, very accurate piece of glassware. Do you guys know what a volumetric flask looks like? Austin, can you go get me a volumetric flask? No, that's a burette. So typically when you're working with these, a lot of times you'll want to start out by adding some water to the volumetric flask first, then add in your concentrated solution, and then fill the thing up the rest of the way with water. Yep, that's the one. Yep. So a volumetric flask is a very precise piece of glassware, but it's only made for one volume. So this one is 500 milliliters. It has a line that's etched here, and that's at a specific temperature. So this one says at 20 degrees Celsius. Volume will change based on temperature. So if you're at 20 degrees Celsius and you get your meniscus right on this edged line, you should have 500 mils of whatever solution that is. So when you're figuring this out, the most precise way is to take one of these burettes. That's the thing with the twisty thing that you were talking about. That's a burette. It's a very accurate piece of glassware. You're going to take that and you're going to measure out whatever you need of your stock solution. Then you add that into here, and then you fill the rest of this up with water until it hits the meniscus on this line. Okay, so if we were to take, this is 1,000 milliliters here. So let's say when I get in my hydrochloric acid, my hydrochloric acid comes in at 12 molar. Okay, So when I get that in, oh, this isn't set up. Okay, so I get my 12 molar acid in, and I've got I want to make a liter of this. Okay, I want to dilute this down until I get to what molarity? Just give me something less than 12.
6.
6, okay, 6 molar. Okay, what I'm going to do is I'm going to use this equation to do that with. Okay, I want to end up with a molarity of 6. I know that I want to end up with, and this works for milliliters, so you can actually throw milliliters in here. I want to end up with 1,000 milliliters, and my starting molarity was 12 molar. I'm solving for V1. So what does V1 equal? You do that in your head? 500, yep, so 500 milliliters. So what I'm going to do is I'm going to take 500 mils of this. I'm going to put it down in to my volumetric flask. Then I'm going to add water until that water hits this etched line. That may or may not be 500 mils. It may be more than 500 mils of water. Because when these things mix, sometimes they don't mix exact. Okay, sometimes there's space between those particles that stuff fits in. And so because of that, if you mix 500 mils of this plus 500 mils of water, okay, you may only end up with 990 mils. And that's not going to work. You've got to fill this up until it hits the etched line. You want a liter because you want to make sure that you have 6 moles of HCl particles in that solution. Okay. So you would measure out 500 mils, and you'd have to do that several times using a burette, because these are only 50 mils. Okay. You're going to end up here with 500 milliliters. You take that, and you're going to put it into here. That's your 12 molar. It's the same thing. Okay. And then you add your water up until it hits the etched line. All right, so just as a safety thing, if you are diluting acids or bases, they end up having a very exothermic process, meaning that they're going to release a lot of heat. So when we do this, typically I will end up putting some liquid, some water in here. So I'll have this filled with some water. I'm going to add my 12 molar in, and then I'm going to finish it off with the rest of the water. It's going to generate a crap ton of heat. Okay. Typically with hydrochloric, I don't have to, but with sulfuric acid, I will usually put the base of this will be in an ice bath because there's so much heat generated that it can actually crack this glassware. This glassware isn't designed to be heated. It's not that strong compared to like your beakers and stuff. And so I actually have to put this in an ice bath when I'm diluting sulfuric acid down, because it will generate so much heat that sometimes it will actually crack my volumetric flask. So you have to be very careful with that. It also gives off vapor as well. And so I always do, anytime I'm diluting acids down or bases, I'm always doing it under the hood because it can get a little scary. Okay, because the steam, you could actually cause a spray of it, and then that can spray back on you. So these are just things, you guys aren't going to be doing this, but it's a good thing to know about if you go off to college and you have to do it. Okay. right, I do. Calculate the volume. If we wanted 1.25 molar lithium chloride, and we have this much lithium chloride crystals. You have your molarity. You've got to convert your grams into what first? Moles. Okay, so convert that into moles. And then you should be able to figure out what volume you're going to be creating in there. How many liters you're going to end up with. All right, so molar mass of this guy is 42.4. So if I divide that out, that's going to give me my moles, which is 0.314 moles. So if I have 0.314 over my molarity, which is 1.25, and remember that this is molarity equals what? Moles per liter. Okay, so then my moles end up canceling out, and that leaves my answer in liters, which is what they wanted. And so when I solve for that, I end up with yes? Did math check out? All right, down here, we're dissolving 10 grams of zinc. Okay, and they want to know what our concentration of this would be. So that would be 10 grams of zinc. It should have been zinc chloride. Does it say zinc chloride on your sheet? All right, sorry. So add chloride in there. My apologies. So first, figure out your moles of zinc chloride and 10 grams of zinc chloride. Oh, the volume here is, this really got cut off. I'm sorry. 500 milliliters. My apologies. I'm going to make this a little bit easier to solve. All right, so when you get this into moles, how many moles is that? 0.073. Yep, so 0.0734 moles of this is going to give us how many moles of these? Four. Right? All right, so that's moles of this. And then we're going to divide that by our liters of solution. How many liters is this? No, 500 milliliters, but we got to have this in liters to figure out molarity. 0.5. Okay. Good. All right. Capital M. Or you can do moles per liter, or you can do moles liter inverse or inverse liters. So you can do it like this, or like this, or like this. All three of these are equal. They're the same thing. They mean the same thing, but it has to be a capital M. You cannot do a lowercase m. This is molality, and this is molarity. Okay, it has to be distinguished as a capital M. Good? Okay. I'm going to skip the we do. If we have time, we'll come back to that, but you can do those on your own, and you're expected to for your homework if we don't get back to them. Representations about solutions then. When we have intermolecular forces, they can oppose the formation of a solution. So sometimes you will have actually things that do not dissolve into solution. And a lot of times your intermolecular forces are going to be what's an issue there. So for example, let's see, I think sheet. I have one. When we did chemistry back in the day, you guys had this chart. Do you remember this chart? Yeah. Okay. So this chart told you whether things were soluble or not. Okay. And if it said N on it, it meant that it was not soluble. So for example, oh, silver chloride, that's a good one. So silver chloride is not soluble when it's put in water. Essentially what's happening is that when you have silver chloride, the interactions, the electrostatic interactions between the silver and the chlorine are so strong that the water is not going to pull that negative ion away from the silver. And that's what's going to make this insoluble. You've got other things like NaCl. When NaCl goes into the water, the chlorine is going to go and be more attracted to the water than it is to the sodium. And the sodium the same way. But here, these two are more attracted to one another than they are the water. So they stay together. So that's what makes one thing insoluble in water and one thing soluble, due to those intermolecular forces. So they're going to exist between solute particles. Depending on the particular solution or solvent combination, these intermolecular forces may either promote, like in sodium chloride, or prevent, like in silver chloride, the ability to go into a solution. The tendency to mix is strong, but if the solvent and solute attractions are strong compared to the solvent-solute interactions, you're not going to get a solution forming. The term miscibility then describes the ability of two substances to mix without separating. So if something's miscible, then that means that it's going to mix. If it's immiscible, it won't mix. This like dissolves like, I better never see this written down on a test. Okay? You can use it in your brain, but don't write it down. Polar solvents dissolve polar solutes, and that has to do with the intermolecular forces. Okay? When we look at a polar solvent, what happens is, like with water here, you're going to have, and a polar solute, you're going to have that material be attracted to the water. If this was oil, though, the water is going to be attracted more to other water molecules than it would be to the oil. So let's pretend that this is oil instead. Okay, oil is going to be more attracted to the other oil molecules. The water will not have any interaction. Here, the heptane and pentane, these are both nonpolar. Okay, they are going to be attracted to one another. They'll be attracted to another thing of pentane or another thing of heptane, but your water will stay together. So your water molecules are going to be attracted to each other, and they're not going to interact with this at all because there's no pull here for the water to pull that towards. So these guys will stay all together, and the water will stay all together. The water's not going to be able to pull these away because there's no negative or positive ion on this to get pulled in. A solution will form if the solvent-solute interactions are greater than the solvent-solute or solvent-solvent and solute-solute interactions. Solution will also form if the solvent-solute interactions are relatively equal to the solvent-solvent and solute-solute interactions. However, if the solvent-solvent and solute-solute interactions are stronger than these, you're probably not going to have that happen. All right, so when we look at particulate diagrams then, one of the other things that they'll show you is like A versus B. They're going to ask you which one's more concentrated. So this guy would be more concentrated than this guy. This guy is going to be more concentrated than this one. This will be a 0.2 molar. So if they said that this was 0.2 molar, they may ask you what the molarity of this is. So if you didn't know that this is 0.1, you could go through and go 1, 2, 3, 4 K and 1, 2, 3, 4 Cl. And then you come down here and you know that this is 0.2 molar. You come down here and you count those and go 2 and 2. Well, and then they say, well, what's the molarity? If you know that this is 0.2, then you'd be able to say, oh, yeah, that's 0.1. That makes sense? All right. So which solvent would be most effective in dissolving the following solutes, hexane or water? And identify the dominant type of IMF present between the solute and solvent particles and draw a particulate diagram showing those interactions. Spend a minute or two doing that. So here you're going to have an IMF between the negative pole of this water and the ethanol. This is polar, okay? So water is going to do the best job here of interacting with this. This guy is nonpolar. Water is just going to stay. If we had water in here, we would just have our water sticking with other waters, and it's not going to let this guy in. It's not going to let him mix. You're just going to have your water sitting here like this. They're going to all stay together, and they're not going to break apart at all to be able to join together in a fashion like this. These guys are just all going to stick together. They're not going to allow in this guy. Okay? And then you can kind of get the idea of the KCl. That would look similar to when we looked at it back up here as far as it getting surrounded with the ions. So we already kind of looked at it here. Okay? So I want 3-7 and 3-8 for tomorrow then, and you have a quiz.